Welcome to This Explainer. Today, we're going to explore the fascinating shift from legacy web APIs to modern, mobile-optimized architectures. If you've ever wondered why your beautifully designed backend system suddenly feels sluggish, fragile, or just incredibly buggy when connected to a smartphone, well, you are definitely in the right place. We're going to look at the very foundation of how data moves, and how the old rules are quite literally being rewritten for the mobile era. So let's dive right into this with a pretty provocative question that challenges the foundation of how so many developers build systems today. Is traditional CRUD failing your mobile app? You know, for years, create, read, update, and delete operations mapped directly and perfectly to HTTP verbs like post, get, put, and delete. It was predictable, it was a comfortable paradigm. But as the mobile device became our primary digital conduit, the limitations of carrier networks, battery life, and intermittent cell service exposed massive blind spots in the standard model. What worked flawlessly on a wired desktop connection is suddenly breaking down right in your pocket. To make sense of this complex evolution, we'll follow this structured roadmap. 1. The mobile API crisis. 2. Put versus patch. 3. Why delete is dead. 4. Intentful APIs and syncing. And 5. Designing for the future. All right, let's start with Section 1, the mobile API crisis, and what happens to CRUD in a mobile world. There's a really fascinating contrast between the simplistic database mapping of CRUD and the scalable, stateless flexibility of REST. You see, CRUD is inherently database-oriented. It's rigid. You're directly manipulating database records. REST, on the other hand, was a massive step forward because it's resource-based and entirely stateless. The server doesn't need to remember the client's state between requests, which is exactly what allows modern systems to scale up. However, here's the catch. Even those solid REST principles face severe turbulence when forced through a high-latency, low-bandwidth cellular network. Which brings us to Section 2, put versus patch when updating data. When you compare these two side by side, it brilliantly illustrates why sending an entire resource with a put request is a massive bandwidth drain on mobile networks compared to the targeted efficiency of patch. With put, if you're updating a user's profile, you have to send the complete representation of that resource. If a field is left out, the server assumes it's gone and removes it. It's a full replacement. Patch, however, is built for partial updates. You literally only send the specific fields you want to change. And on a mobile network where bandwidth usage directly drains your battery life, patch is the significantly more efficient choice. So the absolutely crucial takeaway here is that on a slow 3G connection, you only want to transmit the exact fields that changed, right? Not the entire user profile. Imagine updating a single email address inside a massive JSON object filled with user preferences, metadata, and history. Using put is literally like rewriting an entire document from scratch just to fix one typo. Patch is like just using a dab of whiteout on the mistake. That specific efficiency is exactly what keeps mobile apps feeling fast and responsive. But patch does require careful implementation because unlike put, it isn't inherently idempotent. And idempotency is a totally vital concept for network resilience. In plain English, idempotency means you can safely hit retry. If your phone loses signal right as you send a put request and you resend it, the end result on the server is the exact same. Because patch acts like a set of specific instructions, sending it twice without careful design might actually cause unintended side effects or data conflicts. It's a trade-off, really. You gain massive efficiency, but you have to build smarter API logic to handle it properly. Okay, moving into Section 3. Let's see how this builds into what developers call the resilience crisis, starting with why delete is dead. Executing a hard HTTP delete creates irrecoverable chaos, ranging from major user frustration over accidental taps to outright failing strict compliance audits. Think about the physical reality of using a mobile device for a second. Small screens, touch interfaces. Accidental finality is a huge risk. Users often delete things in a moment of anger, or honestly just by mistake. And for a backend developer, there is almost nothing more terrifying than a hard delete destroying referential integrity and leaving orphaned records floating around the database. Furthermore, if you permanently erase a record, you completely destroy your audit trail. Strict regulations like GDPR or HIPAA absolutely require you to know exactly when something was removed and by whom. So, instead of actually deleting the data, the modern solution is to use an update or a patch to just flag the item as hidden. This maintains absolute data integrity and is known as a soft delete. To the mobile user, the item disappears from their screen perfectly, just like they wanted. But on the back end, the row is simply marked with a timestamp or a little isDeleted flag. This elegantly solves the accidental deletion problem, keeps all your database relationships perfectly intact, and provides a flawless, compliant audit trail. And here's a crazy detail. Because enterprise firewalls often aggressively block the delete method outright, developers now cleverly tunnel their deletions inside standard post requests. Historically, security systems viewed put and delete as really dangerous because they were associated with direct file manipulation on servers. So when a user's phone jumps onto a restricted corporate Wi-Fi or a super strict carrier network, a standard delete packet might just get dropped completely. No warning, just dropped. The industry workaround? Send a post request, which is basically universally allowed, and secretly slip an XHTTP method override header inside it. Sneaky, but highly effective. Now that we've dismantled standard operations, let's explore Section 4, Intentful APIs and the major challenges of offline syncing. The famous Usenex Simba study actually proved that standard synchronization models are incredibly fragile. They frequently result in ghost data when connections drop mid-transfer. Here is exactly why soft deletes are so critical for syncing. Mobile apps rely on incremental delta syncs, essentially asking the server, hey, what changed since the last time I checked? Well, if a record was hard deleted, the server literally cannot tell the phone it's gone, resulting in undeletable ghost records permanently stuck on the device. Plus, if an app crashes while uploading a complex object, like trying to sync a heavy photo to Instagram or a file to Dropbox, standard syncs often leave horribly corrupted partial files sitting on the server. The Simba framework brilliantly solves this by ensuring that structured tabular data and unstructured objects are synced atomically, meaning you never get a dangling pointer. It unifies the local table store and the object store. So when an app syncs to the cloud, it's an all-or-nothing transaction. Either the database row and the image object both make it to the server completely successfully, or neither does. This approach completely eliminates the torn updates and data corruption that plague older traditional sync architectures. Let's step into the final act of our explainer, Section 5, Designing for the Future and Building Resilient APIs. We are rapidly moving away from chatty, fragile database exposures toward encapsulated, intent-driven APIs, where the backend handles the entire transaction in one seamless go. A classic CRUD approach forces the mobile app to orchestrate all the complex business logic. To buy something, the app has to call create order, then call update inventory, then call process payment. If the user drives through a tunnel and loses service right between step 2 and 3, the whole system is left in a broken, half-finished state. Intent-based APIs fix this entirely. The mobile app just sends one clear message, checkout. The server takes that single intent and safely handles all the complex database routing internally. To safely retry these powerful intent-based endpoints on flaky cellular networks, apps pass a unique identifier called an idempotency key, so the server knows not to double-charge a user. Think about that checkout action again. What if your phone sends the request? The server charges your credit card, but the network drops before the server can send the success message back. Your phone assumes it failed and tries again. By attaching a unique idempotency key to the request, the server recognizes, oh wait, I've already processed this specific transaction, and simply returns the cached success response. It guarantees exactly once execution. By combining these hyper-reliable endpoints with what's known as an optimistic UI, apps can instantly update the screen while handling the actual network call silently in the background. Because we now have total confidence in our background syncs and retries, we don't need to force the user to sit there staring at a loading spinner. The app optimistically assumes the action will succeed, eagerly updates the interface instantly, and does the heavy lifting of API communication out of sight. If something catastrophically fails, it simply rolls the state back and quietly notifies the user. It's a real game changer for the user experience. And you can supercharge this entire process by replacing bloated JSON text with protocol buffers, slashing your mobile payload size by an astonishing 80%. JSON is great because it's human readable, but it sends massive amounts of repetitive metadata over the wire. Binary formats like protocol buffers, or protobuf, use predefined schemas to compress this data down to its absolute bare minimum. Less data means way faster transmission times, less parsing work for the phone's processor, and a massive, massive boost to your user's battery life. I'll leave you with this final, provocative thought to challenge your own architectural choices as you build the resilient, intent-driven apps of tomorrow. Is your API speaking to a database, or is it speaking to your users? Because as we've explored today, exposing raw database operations like CRUD and hard deletes to a mobile client is just a recipe for fragility. By shifting to highly efficient patch updates, safe soft deletes, intent-based logic, and atomic synchronization, you stop treating the mobile device like a wired desktop and start delivering the seamless, resilient experiences your users absolutely expect. Thanks for joining me on this explainer, and I hope this completely changes how you think about mobile data.